Assalamualaikum. Today's lesson is a revised excerpt of a past upload on single-slit diffraction. Specifically, we analyze a problem that involves Fraunhofer diffraction. So join me till the end of this video. Watch and learn. The question is, you pass laser light of wavelength 645 nanometers through a slit 0.250 millimeters in width and observe the diffraction pattern on a screen a large distance away. On the screen, the centers of the second minima on either side of the central bright fringe are 28.0 millimeters apart. The questions are: letter A, how far away is the screen? And question letter B, what would the distance between these minima or dark fringes if the wavelength were 525 nanometers? Right? So in the single-slit diffraction experiment as given in this illustration, we can observe the bending phenomenon of light or diffraction that causes light from a coherent source, such as laser light, to interfere with itself and produce a distinctive pattern on the screen called the diffraction pattern. Diffraction is evident when the sources are small enough that they are relatively the size, the wavelength of light. In other words, when the barrier here has a very or relatively very small width for its opening, comparable to the wavelength of the light source. Again, we emphasize that the behavior of waves after they pass a slit is an example of diffraction. Each infinitesimal part of the slit acts as a source of waves, and these waves do interfere, producing a pattern of bright and dark fringes on the screen. The nature of this pattern depends on the color or wavelength of the light and the size of the slit. In this problem, we are given the wavelength of the laser light, lambda sub 1. All right, this is for question letter A. So the wavelength of the laser light equals 645 nanometers, or that is 645 raised to the negative 9 power meters. And for question letter B, we change the wavelength. So it's now lambda 2 equal to 525 nanometers, or 525 raised to the negative 9 meters. All right? So let it be understood that the laser light is considered a coherent and a monochromatic light. So it is made to pass through the slit or the small opening in the barrier, all right, whose width denoted by small letter a, is equal to 0.250 millimeters, or that is 0.250 raised to the negative 3 meters. On the screen, a few meters away from the slit, you observe the diffraction pattern. And the distance denoted by letter Y, all right, this represents the distance between the centers of the second minima, or dark fringes, on either side of the central bright fringe. And this is given as 28.0 millimeters. So, half of that, or 14.0 millimeters, is the distance y sub m. All right? Y sub m is the distance from each second minimum to the center of the central bright fringe. Right? Take note, the central bright fringe is denoted here by capital M. Right? Although this is considered as or being equal to 0, it doesn't mean that when you say central bright fringe, all right, it doesn't mean that this is a dark fringe. In fact, it is considered the central bright fringe, or um, the result of constructive interference of two waves, all right, that are in phase. So it has the highest intensity, and therefore is considered the brightest maximum, or bright fringe. For question letter A, we are asked to find the value of x, that is the distance between the screen and the slit. While in question letter B, we are asked to find the value of y, or the distance between the two second order dark fringes. All right? If the wavelength of the laser light is now equal to 525 nanometers. So take note that y is twice the value of y sub m, right? Where y sub m is the distance between the center of the dark fringe and the center of the central bright fringe. And its derived formula is given here as x times m times lambda divided by a, where of course x is the distance between the screen and the slit. Small letter m represents the dark fringes, also known as the minimum. So for the first order minimum, m is equal to plus minus 1. For the second order minimum, m is equal to plus minus 2. And for the third minimum, m is equal to plus or minus 3, and so on and so forth. All right? So this equation is applicable for cases where y sub m is pretty much less or smaller compared to the value of x. And it is commonly known as the Fraunhofer diffraction, or a far-field diffraction. And this is the kind of diffraction that we are describing in this problem. All right? This is a case where the rays that are produced, okay, as they pass through the slit, Okay, they are assumed to be parallel when they strike the screen. All right, as differentiated from what we call a Fresnel diffraction, also known as a closed field diffraction, where we assume that the screen is relatively close to the slit such that the incoming rays, all right, passing through the slit as they strike the screen, they are not parallel, but rather they tend to diverge. So we call that the Fresnel diffraction. So moving on now to our computation. For letter A, okay, finding x using this formula. X, or the distance between the slit and the screen, that's equal to y sub m times a divided by the product of m and lambda. So when we plug in the given quantities into this formula, we have 14.0 times 10 to the negative 3 meters. That's the value of y sub m multiplied by 0.250 times 10 to the negative 3 meters. All right, that's the value of A divided by twice the given wavelength, or 2 times 645 times 10 to the negative 9 meters. So doing our math, we will get the value of X equal to 2.71 meters in 3 significant figures. All right, so in other words, the screen is 2.71 meters away from the slit. And similarly, for question letter B, where we are asked to find the value of y sub m, all right, or the distance between the second order dark fringe from the center of the central bright fringe. And that is equal to xm lambda divided by a. So again, substituting the given quantities, y sub m equals 2.71 meters. All right, that is the computed value of x. And then multiply it by 2, since we are talking about the second order minima. And then times the wavelength of the laser light, 525 raised to the negative 9 meters, and then divided by the width of the slit, 0.250 raised to the negative 3 meters. So finally, when we do our math, we arrive at the value of y sub m equal to 1.77 raised to the negative 3 meters in 3 significant figures. But since what we want, or what is asked in question letter B, is the value of y, all right, y being the distance between the two dark fringes on either side of the bright or central bright fringe, all right, and that is twice the value of y sub m. That is, y equals 2 times 1.77 raised to the negative 3 meters. So we get y equals 3.54 millimeters, also in 3 significant figures. All right. So this is the distance, or computed distance, between the two second order minima or dark fringes. So that's it. We are done. Till the next episode, mabuhay. Masya Allah. Thank you very much for your indulgence. Alhamdulillah. Please follow me in my FB page, Watch and Learn. And if you haven't subscribed yet to my YouTube channel, please click here.